Okay, welcome. Welcome to our first virtual chapter meeting of the OWASP Belgium chapter. We're very happy to welcome Jim Manico, all the way from Hawaii. It's very early in the morning for him. Hi, Jim. And Jim has a surprise co-host with him, all the way from Belgium, Philippe Derrick, and they're going to entertain us in the next coming hour on JSON Web Tokens, signing like it's hot. So we're looking forward to that. Just a short heads up for the next couple of months. So this is first in a series of virtual Belgium chapter meetings. Each third Thursday of the month at 17 hours local time here in Belgium, we'll have OWASP leaders bringing a topic here. So make sure to save that date and those time slots in your agenda. Also, make sure to join our channels. So we've specifically for this created the first YouTube Belgium chapter channel. So we'll be publishing this afterwards. Join us on Meetup, on LinkedIn, on Twitter. And then with that, I'll give the word to Philippe and Jim. Take it away.
Wonderful. Hello, everybody. Thank you so much for being here today. It's really my pleasure to be speaking with you about JSON Web Tokens and how they've radically affected application security. My name, by the way, I am Dr. Philippe Derrick. I'm a professor from University of Leuven in Belgium. I'm from Belgium as well. And it's really a pleasure to be here. Okay, I am not Philippe Derrick. I am Jim Manico. And I brought, and let me explain why I'm bringing in Philippe. So I think of an OWASP chapter meeting as like a casual meeting, like you're inviting me over for beer. And if you invited me over for beer, what would I bring? I would bring beer myself. And what kind of beer should I bring, Seba? Hey, Seba, if you're, hey, Jim, come over for beer. And I came to your house for beer, what kind of beer should I bring? Should I bring German beer? No, I should bring Belgian beer. That is why I invited Dr. Philippe to speak. Dr. Philippe is one of the most world's renowned experts on JSON Web Tokens. And I don't say that lightly. I've watched Philippe in his career go from coming out of university as a professor, having a great academic knowledge, and watch him little by little really dive into the industry. And just like a couple hours ago, I'm watching Dr. Philippe work with the standard bodies and like debate with the heads of these standards around how to clarify their standard. So I've had a chance to watch his own progression, and there are very few people who can argue with the Neil Maddens and Bradleys of the world who build these standards, and Philippe does, to all of our benefit. So that's why I brought him in here. And as a bunch of folks from Belgium, you should be very proud of Dr. Philippe. He's one of the few professors who has a PhD in web security. And you know Leuven University, it's not like some American junk university, it's a real university. So you should be very proud of him.
That's why I'm not a professor either. It's not because you come from a university that you can call yourself a professor here, but let's just stick with doctor and web security expert. That's fine for me.
Well, Dr. Derrick, it is a big, you're my friend, and it's a big honor to have you here. Enough ado, let's get to work. Next slide, please.
All right, sure. Here we go. Blank canvas. So let's talk about JSON Web Tokens.
So what's this? This is Mike Jones. Mike Jones from Microsoft, Bradley from Ping. There's Nat Sakamura himself. These are like some of the most prestigious identity experts and standard writers in the world right now. Heavy duty people. Keep going. What else we got?
That's where JSON Web Tokens come from. It's a spec basically. And everybody thinks like, yeah, how hard can it be? It's a JSON format and some signatures. But if you look deeper, it's like a whole suite. You have JSON Web Tokens, you have JSON Web Encryption, you have 7515 is signatures, and JSON Web Keys. And there's a spec on that. I can keep going. It's like algorithms and so on and so on. So in a nutshell,
can I ask you, when you look at all of these standards from a high level point of view, philosophically speaking, what is your how could you express your feeling of these standards with an emoji, for example?
Yeah, I would say it's a dumpster fire. So something like this makes perfect sense. If you look at problems with JSON Web Tokens today, it's an absolute nightmare. So it turns out that having a dozen of specs for something that seems simple is not the best idea. And that's what we're going to talk about today. Common problems, how to do things right, most specifically.
If we had 12 specs to solve I didn't mean to interrupt you, Doctor. No, go ahead, Doctor. I didn't mean
No,
to
no.
interrupt.
I was just going to say we're going to talk about things you shouldn't do and things you definitely should do. So that's what this is about.
And when you have like 12 standards, how do you fix that problem? You just add a new standard to roll them all up into the new standard. All right,
that's for the end. That's the conclusion part. We're kind of spoiling it here. All right, so let's move forward. This is not Jim. We kind of established that. So Philippe Derrick from Belgium. If you want to look me up, you can find more on my website called pragmaticwebsecurity.com. I mainly work with companies to help them build more secure applications, training, consulting, online courses, whatever is necessary. Of course, you have Jim, who will introduce himself aptly, I'm sure.
My name is Jim Manico. I do AppSec. All right, I'm done. I'm done with my intro. Let's get to work here.
Awesome. So we have a couple of things here. I'm not sure how far we'll get once we start going back and forth. So I cut it up in a couple of pieces. I would say we should pick one and start. We can start at the beginning, or we can jump to some of the random things. Probably not a summary. Where do you want to start, Jim?
Let's talk about the signature trade-off. I think that's a really important place to start because, first of all, JSON Web Tokens require a digital signature. Why is that? Why? Because I heard someone several years ago tell me all of identity is moving to a digital signature. And that really made no sense to me several years ago until I started studying microservice architectures, JSON Web Tokens. Now it all makes sense. So this signature is now the absolute critical focal point of all of modern identity, is verifying a JOT signature. Because the whole reason why JOTs have a signature is for the purpose of integrity. Not so much non-repudiation, but more for integrity. We do not want the attacker to be able, who has access to a JSON Web Token, to edit it. If they can edit a token, that's like editing a live session. I'm going to be an admin. I'm going to be Philippe. I'm never going to expire. And so we have to make sure that when we hand a stateless client represented by a JSON Web Token claims, that there's no way for an attacker to modify it. And Philippe, what's the default standard signature type for a JOT?
Well, what you'll find typically is called an HMAC. So in essence, it's where the blue part here. So this is a tool called jot.io where you can decode a JOT, which is the blob on the left, and you get the three parts: a header, a payload, and a signature. And in this case, the signature is an HMAC. So you want to talk about how an HMAC works? I have a very nice overview slide to discuss that.
Yeah,
so with an HMAC, the HMAC is calculated over the data of the JSON Web Token. And the data is in essence the header and the payload. So you feed that into an HMAC function. Well, a library does that for you. You don't do that yourself. A library does that for you. And you give it a secret key. And out of that function comes an actual HMAC, which is, well, it's random chunk because it's not intended for human consumption. But essentially, it's associated with that data and that key. And that's what we attach to the JSON Web Token. That's the blue part. And that's what you send wherever you want to send it. If it's to a client, to another service, that's essentially the full JSON Web Token that you send around. And that's awesome. And that will give you integrity protection.
And this is from the hashing family, right? We have message integrity codes like SHA-1, SHA-2, SHA-3. This is a message authentication code. It's basically like normally you would just hash a piece of plain text. Now we're just hashing a piece of plain text with the secret key. So in order to achieve the same hash value, we have to have that key in the same data to get back to it. So it's going to provide integrity similar to a hashing algorithm with an added key round. So it's no longer predictable. It's now derived from that key in some way.
More importantly, if you're an attacker without a key, you will not be able to generate a valid signature. So whenever your application receives an HMAC signed JSON Web Token, what it's going to do, or what a library is going to do, is going to recalculate that HMAC, take the same data or the data of the JOT as input, the secret key as input, and out comes the HMAC again. This is not rocket science here. What's going to happen then? We compare the values. We compare the signature that was attached to the JOT to the HMAC we just calculated. And if these are the same, that's good news, because then the message was the same as the one that has been signed before when the JOT was created. And if these are different, that's generally bad news in the sense that we don't want that token because something is wrong. We don't know what. Maybe the data is different. Admin has become true, which was not supposed to happen. Or the key is or the signature is wrong, or the key is wrong, something is wrong, and that's when we kick out that token essentially.
And this is so important for next generation microservice architectures, because we can't have a central session that's effective from a performance point of view when you have 100 or 200 services. Like if every service in your microservice mesh needed to verify the token against a central store, you can kiss performance and scalability out the window. So this HMAC is a way to sign a JSON Web Token so I can pass it around a microservice mesh, and just by having a copy of the key, I can verify that token without needing to without needing to request to another service to check if that token's active. This is a stateless, self-contained, usually a bearer token with all the information I need to check a user session. And like Philippe just said, if I change 1 bit on the data, or if I change 1 bit on the HMAC integrity stamp, let's be pedantic. These are not signatures. These are integrity stamps. They're not formal signatures. We're going to call them signatures for the sake of this talk, but just be a little pedantic.
Yep.
The
JOT spec calls them signatures as well, but that's in a crypto world that would be very inaccurate. But for this discussion, that's good enough.
I'm with you. So when you change 1 bit on the signature, change 1 bit in the data, and the HMAC doesn't match. We love it.
So how do you verify the HMAC? Let's look at a Java code example. There's a library called JavaChat. That's as easy as things get. And here's a nice code example. So you like that?
No,
Jim from Hawaii?
This is offensive to me, Dr. Derrick. This is super offensive, because a lot of the folks who drove these next generation standards, OWASP 2, OpenID Connect, and JOTS, they're not web security experts. They're identity experts. So a lot of classic web security mistakes are made in these early standards. When you're pulling a token from a URL, you're probably playing around with OWASP 2 or OIDC. And what's the first rule of web security? You don't put sensitive data in a URL, because it leaks through logs, through refer headers, it leaks through bookmarks and browser history, and URLs, even over HTTPS, are super leaky. So when you're pulling a high-end identity token from a URL, not always, Philippe, like you've told me, but sometimes that's a giant risk to your software that's not good.
But why do you think this is a sensitive token? A JOT is used often to represent sensitive tokens like access tokens, but in essence, it's just a piece of JSON data. So you could just as well have public data with a signature and get that from a URL. So that's a common misconception, is that JOTs must be sensitive tokens, but it's just a way to represent JSON claims with integrity and some form of authenticity through possession of the key. But that's all it does. But there's a bigger problem here. We got stuck at line 1. So I would argue, if that's a sensitive token, that get token from URL is not the right function to use. But what's the second problem here?
There's no signature. You're just decoding and using it. I don't see any kind of signature verification step. Where's your signature verification, doctor?
Well, in this case, I don't know. We have to look up the documentation of this library to figure out that decode is basically just parsing the body of the JSON Web Token, doing a base64 decode, parsing the JSON and giving you an object with the claims. But this is dangerous code, but it doesn't really mention or make this very clear, the library. It's just like, decode and we're good. But it should have been like decode without verifying signature, or insecure decode, or something like that, because that will trigger a developer doing autocomplete like, hey, wait on, why is this not verifying the signature? And that would have been a better pattern in this case.
Like dangerously set HTML, or the bypass security in Angular. These are known dangerous functions that are labeled as such. And this is a mistake in this, a lang-sec mistake in this lib. I got you.
Absolutely. It's a small hint that can help a developer build a more secure application. So what you should do is something like this, at least if you're using an HMAC. Something more like this. What we're doing here is we're basically building a JOT verifier. That's how the library works. And we're actually giving it the secret, which should not be the string secret, but you kind of get that. The actual secret key for the HMAC, and we're going to verify the JSON Web Token. And this will actually complain if the signature is invalid, and checks a couple of other things as well, like expiration dates and stuff like that. But this is essentially how you would verify an HMAC-based JSON Web Token in a simple Java application. There's a bit of a problem with HMACs though. Let me skip back to this image here. You mentioned like, yeah, you can generate HMAC-based signatures and just throw the JOT around and everybody with a key can verify whether that token is valid. But if everybody has the key or every service has the key, then what else can they do?
Anybody who has an HMAC key, well, they can verify, but they can also create. So if this is the problem with HMACs. This is why, in Philippe, this is why it shouldn't be the default signature type in any standard, because it makes the burden of key management ridiculously more difficult. And when you move JOTs, that key, like Dr. Philippe, are you familiar with the Lord of the Rings by any chance?
Yes, like I hate it.
Hobbits. How would you describe an HMAC key in the language of the Forgotten, in the language of Lord of the Rings? How would you describe?
Well, honestly, I don't know. I never made it past the first 30 minutes, and then
it's okay.
I did something useful with my life.
It's the one, like in the Lord of the Rings, we have the one ring to rule them all. Well, in HMACs and in microservice architecture, it becomes the one key to rule them all. And I need to take this key and distribute it to every single service. And if any one service gets key management wrong and I can steal it, guess what? I can now create my own JOTs from scratch, and it's game over.
I've heard people say at conferences like, yeah, if a third party needs to verify your JOTs, just give him your HMAC key. And I was like, no, you don't. No, you don't. There's some other problems with HMACs as well. So first of all, that secret key is typically a string. And if somebody has that string, if it's in a code repo or on your PowerPoint slide here, that's probably a bit of a problem. And this is something that we observed, or some researchers observed in practice. So there's a tool called JOT Heartbreaker. And it basically has a list of known JOT secrets, like from presentations and blog posts and so on. And they can automatically try if a JOT that you captured from an application as a pen tester uses one of these secrets. And they ran this and they discovered that people actually have production applications with secrets from a blog post. It's like, oh, here's a tutorial on JOTs, copy, paste. Oh, this works, done. And this is absolutely insane. Absolutely insane. And it goes beyond that. It goes further because an HMAC is guessable. It's a string, right? Maybe it's a random string, but even then, if you have a year or two, you can actually break an HMAC secret because it's just trying out combinations until your HMAC matches the HMAC of the JOT. And at that point, I have your secret. And this is something we've been struggling with for a while. And to be fair, the spec, first of all, doesn't say that JOTs are signed by default with an HMAC. It's just what everybody does because it's easier.
Thank you.
But the spec also says use a decent HMAC secret. Use at least 256 bits for an HS256 algorithm, because that will make the guessing of the key virtually impossible or way too difficult. But to wrap up the HMAC discussion, because that's where a lot of the JOT talks stop, HMACs are absolutely useless except for one case, and that's an isolated service. If you have one service generating JOTs, throwing them over to someone else and getting them back, it's their own JOTs, then you can kind of use an HMAC, but otherwise you should definitely avoid using HMACs.
And Dr. Derrick, I know it's a bit tangential, but one of the big use cases for HMAC signatures in this family of technologies is with the BFF pattern, where I want to have basically a session between the client and the gateway, and then only use access tokens, hopefully they're JOTs, on the back end inside the microservice hierarchy. So between the client and the API server, it's not quite a JOT, I know, but it's similar technology. I may have a reference to a JOT that has a session ID in it that's also signed by an HMAC, because the only person who needs to verify that token is the gateway. So in that situation, the benefit I get is like nobody can even tamper with the session ID anymore because they can't sign it themselves. So it's a little
that makes a lot of sense, but usually you'll find that pattern in libraries like I think Express Session or Cookie Session for Express, and Happy has the same library, and they do that kind of concept, but they use cookies for that. So they put a session object in a cookie, and it's not a JOT per se, but it uses the same mechanism. So it's a data structure with an HMAC attached to it. So it's exactly the same mechanism. You could do that with a JOT, but that would be, unless there's a specific reason, I wouldn't say that's very useful. But yeah, session objects with HMACs, that happens quite a bit in practice.
Absolutely.
But there's a much better signature scheme, and that's using real signatures, so actual digital signatures. And with that, let's walk through the same scenario here. You have the data, the header and the payload, and you generate a signature using a private key, which comes out of that cryptographic function. You don't write that yourself, and you attach that to the JSON Web Token. That's typically the RS-256, but you're better off using PS-256 if you have to choose an algorithm anyway in the JOT world.
Can you highlight that one more time? I usually mention RSA as an asymmetric signature type, especially in Europe. I get a lot of folks complaining about, less so in America, but especially in Europe, folks have moved beyond RSA for asymmetric signatures. Do you agree with that? Or?
There's a difficult trade-off between the best algorithm and library support. So
Gotcha.
The bestest algorithm is probably based on elliptic curves, but some options have good library support but are very difficult to get right. Other options are much better but have limited to no library support in a JOT world. So RS-256 is basically plain old RSA signatures. These are considered to be secure, but there is a spec, an RFC from the crypto people that says like, yeah, we kind of want to move away from this because we expect this to start breaking in the coming year. So here's a better option. I don't know the full algorithm because it's quite long, but it's in the JOT world, it's PS-256. It's also based on RSA keys, but uses a different, I think, padding mechanism and signature mechanism. So it's still based on the same keys. You don't have to change anything except the algorithm choice in your application, and you're done. That's PS-256. All right. Pop quiz, Jim. I'm sure you can manage this one. How do we verify the signature here? What do we do?
Okay, verify this signature. I'm taking the same data, and I'm using the public key to verify.
Absolutely. So we have a verification function in our crypto library or JOT library. We feed it the signature, the data, and the public key, and it will spit out a result, true or false. No error or exception, whatever your language prefers doing. And that gives you some information. If it's valid, then you know that the message is the same as the one that has been signed. So nobody changed anything about it. And also very important, it has been signed by the private key that belongs to your public key or the public key you're using. So I'm using Google's public key and the signature is valid, then I'm pretty sure that has been signed by Google's private key or that Google is in a world of trouble because somebody is running around with their private key. And if something is different, then we basically have a choice. Well, a choice, we throw it out, but it can be because of the data has been changed or because the key doesn't match, something is not right. So we do not accept that token. And this mechanism is what we should use by default for JSON Web Tokens. Forget about HMACs, implement public-private key signatures because that's a lot better.
It minimizes your key storage burden. Now, I only need to really spend the money on like a HashiCorp or CyberArk or your cloud-based key management solution. And now I only have to spend that money in one service where the user logs in and I create the initial key. And are we going to talk about the key management struggles later in our talk, Philippe?
If we get to that, yes, sure.
Let me make a quick note, just a quick note on this. When you go back to the previous slide real quick and I'll let it go. When you're doing this key management, if your code can access the key, the private key, I believe that's a failure. The real way to do key management is to put it in either a secrets management solution or vault where your code sends the data into the vault. And that's where the signature is done without exposing the key to the source code. And this is the most fundamental principle in doing key management properly. Azure, GPC, Amazon, they all support this. If you use like Azure for your login service and you ask for the private key, I don't care if you're paying 50 million a minute, they are not going to give it to you because it's isolated in an HSM, and distributing that private key is a mammoth danger. Just a quick note on that.
Yeah. HashiCorp Vault doesn't support that, by the way. So HashiCorp Vaults, they do secrets management, but they don't support crypto operations on the vault itself.
So
but the cloud-based solutions do.
So what we can do, though, is we can build one small private isolated service that uses HashiCorp as opposed to deploying HashiCorp native in certain services. So we can still do that isolation on a separate service. That's really simple. But that key isolation, which a lot of us don't do, I think is super critical to get this right. I'll let it go. I'll let it go, Philippe.
Absolutely. So if we have these asymmetric signatures, that's where we can build something like this. And that's what this is kind of a simplified case of what you see in the world of OAuth and OpenID Connect and all of these things. So you basically have a client looking to access an API. We're going to request a security token from a central service. Let's call it a security token service. Your authentication endpoint, if you handle authentication internally, your authorization server, whatever you're building. It's going to generate a JOT, sign it with a private key, and send that JOT to the client. And that JOT can now be used to access an API, which can verify the JOT with a public key, which is publicly known. That's kind of the point of a public key, and make its authorization decisions with tokens like this. And this is exactly what you'll find, or what you should do if you want to use JOTs, because the client should have, or there should be some level of control at the security token service of when you want to issue JOT tokens. You can keep their lifetimes fairly short and rely on a session between the client and that security token service for maintaining some kind of a session concept, whether that's a client-side session or server-side session. But that's essentially a oversimplification of what OAuth would do to issue access tokens as well. Are we good?
Charge.
All right. So that brings us back here. Overview. What do you think? Shall we talk about some ridiculous JOT vulnerabilities and maybe a demo with that?
That's I say we fail on key management. We hit the core principles there. Let's go. Let's show me something ridiculous. I want to see ridiculous.
All right. Let's talk about JSON Web Token some more. What do you think? Is this a valid JSON Web Token?
Algorithm none, type JWT. I don't know I know the algorithm and type are standard claims. I don't know if KID is a standard claim or not. I don't know about that. But yeah, none is a great algorithm. I mean, it's great for testing and debugging when I just want to make it rock. But I really would, and these are standard claims, issuer, expiration time. Yeah, this is a fully legit token that completely skips the signature.
So this is kind of a compression mechanism, right? It keeps your tokens shorter because you don't have a signature. It's awesome. It's really,
so
really
much easier to deploy. It's so easy to deploy. Key management's not a problem. This is awesome. Let's do it, baby. Push it live, baby.
Yeah. So the problem here is twofold. First of all, the KID is a valid claim. It's meaningless in this case, but it's valid. But the ELG none here is actually valid. If you go into the spec, the JSON Web Signature spec, there's none saying this token is not signed, which means that this is a token without integrity protection. So anyone can modify this data. So nobody is going to create tokens like this, right? I mean, developers are not idiots. I trust developers in building solid software. So if they see this, they're not gonna create tokens like this. But if you don't create them, what about your API accepting them? Is that still a problem?
That's the problem.
It turns out that back when they built JOT libraries, that for once libraries follow the exact specification, and they had a code path in the library that says, hey, if there is no signature and the ELG is none, that's all cool because this doesn't have to be checked anyway. So accept that token and move forward. And this resulted in the fact that your service using a library like this would accept any arbitrary JSON Web Token with ELG none. And that's a bit of a problem. But hey, it's 2015. Like, come on. 6 years ago, how relevant is that today? Well, it's one example. OutZero's Authentication API, so their internal APIs that you can use to manage your clients, was bitten by this exact vulnerability in 2020. So that's a really, really nasty vulnerability. And to make it even more recent, there is an application in the UK called the NHS COVID-19 Contact Racing App, which I'm pretty sure is only fairly relevant, like recent, like nine months ago, something like that. And even there, you find a vulnerability like this. So it's not a 2015 problem. It's a problem we find up to this day. Well, this is from a couple of weeks ago, this screenshot. So it's probably going to be a bit more days, but it's still the same vulnerability. But there's a website to track how many days since an ELG non-vulnerability.com. It's really, really that bad. And attackers are actively abusing that as well. And I want to show you a quick demo of how this would work in practice, because demos are always fun, especially when they work. So let's see if we can make this work.
And real quick, Doctor, I feel like this is a flaw in the standard. I do not think JOT should be self-declaring their signature type. I endorse headless JOTs where the server enforces signatures but the JOT itself should never declare it. This is a nonsense part of the standard, in my opinion.
Well, headless JOTs are not very useful, but we should not rely on that ELF claim for sure. That's not a good idea to do. So in the demo, I have a small Express application, Node.js. It's as simple as it gets. And we're going to run a couple of things. I'm going to run things through Burp because I'm going to show you how to use Burp to attack an application of your own, not someone else's application, but your own. And since we're talking about JOTs and APIs, I'm going to run things in a terminal because that's quick and dirty. And I'm not the best UI designer either. What I'm going to do here is I'm going to send a request to our backend running on localhost 3000, of course. I'm going to log in with a username and a password, and we're going to tunnel things through Burp for later. So when we do this, we're basically submitting a username and password, and we get a JSON Web Token in return. So this is a JOT token coming from our security token service or endpoint, whatever. And if we inspect this, let's do that right here. If you would go to jot.io to inspect this token, we can see what's inside that token. So we can go here. Apparently it's loading. Yeah, there we go. And we drop the token here. We can see it's a JOT token signed with HS256, an HMAC. We have a user identifier in here, 1, and we have the signature. Very simple like that. So what we can do now is we can send a request to another endpoint to get profile information. So let me do that. Do /profile with the token in an authorization header with type bearer. That's how we would commonly use JSON Web Tokens in an application. And you can see that it comes out and we get our bio information. It's very non-populated, the data, but you kind of get the idea. Let's just for kicks, let's modify something here and see what happens. If we do it like that, then you'll get an error. So the application is actually verifying the signature on the JSON Web Token. And if you look at the code, this is the profile endpoint. If you would look at the code here, it says like, hey, if there's a token, verify that token with the HMAC secret. Throw an error if there's something wrong. Otherwise, you can actually look up the bio information and send that back to the client. All right, that's the setup here. So this looks good. If you would edit and audit this code, you will see like, hey, secret is being verified. Everything looks good. This is perfectly fine. However, if you don't test it, then you have no idea what your application is doing. So let's run a couple of tests manually. And of course, you can automate this. This is Burp. If you don't know Burp, Burp is a tool used by pen testers and hackers alike to essentially analyze HTTP traffic and mess around with that traffic. And what I've done in the terminal is I've sent traffic through Burp so we can inspect our requests from before. You can see the login that we did and the response that we received. And we can also see the GET requests to get profile information. This is where things get interesting. Now we can use this and send it to the repeater. And the repeater is a tool where we can modify the request and send it out again and see what the response is. So if you would send this, we would get a response, and the response basically shows us what we have. Not very special, but this is where things get really cool. We can now start playing around with this. So I installed an extension to mess with JSON Web Tokens, just a Burp tool available here, and it will decode the token for us. You can see the claims here and so on. So now we can start editing this. Let's make this 2. What if we can get a profile for another user? If we send this request, we get a response back and it says like, oh, failed to verify. That's your HMAC kicking in. Your HMAC is attached to the token and the server says like, yeah, but this doesn't match. This is not valid. I'm not going to accept that. In this case, the Express application here uses an old library like pre-2015. So I'm going to show you what that vulnerability really means. We can now select ELG none. This will make our JOT an ELG none JSON Web Token. We have our UID set to 2, and we can send this request. And the response here gives us data. It doesn't complain. It now just gives us the data for user number 2. And if we would look at the request, the raw request here, and look at this token, you can see that there's no signature present. And if you would, the last part is missing. And if you would decode this in a browser, let's do that right here. That is, it's base64 encoded, so we should be able to do it like this. You can see that the token actually contains user ID 2, and the backend accepts that. So this is the exact vulnerability that exists in every application using a library from pre-2015 or if you use your custom code that has a code path for ELK none.
Yeah,
so let's,
Doctor,
yeah.
This is what upsets me so much is that the libraries have fixed this 5 years ago, and I don't see many people at all doing this manually in their own code. So how could someone like the British government get this wrong? And I'm not just picking on the Brits. This is everyone how come these problems are still prevalent in critical services when 5-year-old libraries have this fixed? I don't understand that.
Yeah. Well, it's a nightmare. Absolutely. I don't know what happened in the UK, but I know that they ran their first contact tracing like in Excel, and they ran into limits of a number of Excel records or something like that. It's ridiculous. But that aside, what you'll find, and the Auth0 vulnerability demonstrates that, is they didn't accept none. So Auth0 had a check in their API that says like, hey, if ELK is none, we don't accept that. So I've implemented this code right here to basically get out the ELK claim in a very dirty way and check it against none and make sure that this works. So let me restart my Express application right here, and let's see what this does in practice. So we have our request.
Philippe, wait, what a horrible way to solve this problem. Even if they did it case insensitive, this is classic blacklisting, which is a bad security technique. I mean,
well, stick with me. I'm walking through the process, but yeah,
it just hurts me. Right. It bothers me. Philippe, why are you doing this?
But because it works. Look at this. We send the response and it says like, ELK none is not allowed. So problem solved.
No. No.
Seriously, this sounds ridiculous. If I do it step by step, you're like, yeah, nobody does that. But there have been cases for command injection. Somebody reported a command injection vulnerability on a Cisco system, and Cisco's patch was to block the curl user agent. I'm not joking. I'm not joking. I didn't see her drinking there, so that was a close call. But that's not a joke. So these patches happen in practice, and I want to show you why they're a very bad idea. So this seems to work, but of course that's without. Let me check my scenario here. That's without the actual check. So without the
it's effed up.
Yeah, it's without taking into account that we can actually do none with case insensitive. So if you switch this to none like this and send a request, and it works again. And we can keep doing this. And this allows us to call the post endpoint, and I'm going to cut it off here. What I want to do is I want to show you why this problem shouldn't be there in the first place. So let's fix or remove our fix. And let me show you what we should have done instead. So let me pull up this terminal window. And this is my Express application, very simple in index.js. And if we would run npm audit or a sneak test or whatever tool you're using for package management, it will actually complain. It's like the simplest package.json. If we look at package.json, my apologies, we have like a couple of dependencies, and we have 6 vulnerabilities with a lot of problems here. And if you would actually update our libraries the way we should do that regularly in our real applications, the problem would go away as well. But that's exactly what happens. People build something, they deploy something, and these vulnerabilities really don't get fixed if you don't update or keep your packages up to date. So if you would restart this now, then the problem should have gone away altogether. So if you can go back to burp, we can send a request and see like, oh, it's actually rejecting them now. Let's try something else with this one. And you will see that these things are stopped in practice.
Awesome.
But the steps I've shown you here are steps that people actually take in practice with the exact problems as we have discussed them right here.
That's wild, Philippe.
Yeah. All right. So what we have here is, this is the tool called JSON Web Token Attacker. That's what Burp Suite uses, or what Burp Suite has available to mess with these tokens. And my recommendation here, and this is really important, you need to do this yourself in a test suite as well, not just manually with Burp, because that's not sustainable, but you need to have test suites that verify how your application behaves. I don't care what you think your code does, unless you test this in your libraries, you don't know how your application is going to behave. I've showed you this. The code looked perfectly fine, but just depending on what version of a library you have, it's a problem or it's not a problem. And that is something that you have to test for.
Dr. Derrick, I have a class in 20 minutes. I'm going to politely bow out and say thank you for being here. Let you finish the talk. I know you got it. Thank you so much for joining and letting me bail early so I can get to my class. And thank you for teaching us about JSON Web Tokens. I love you all. It's all yours, Philippe. I'll talk to you soon, everybody.
Thanks, Jim.
Thank you, Seba.
Thank
you, Seba. Thank you for what you do for the foundation. I love you, and I appreciate all you do for us, Seba. Thank you.
Aloha.
All right. So let's talk a bit about the other topic we have in store, and that's essentially how we can handle key management in a bit of a cleaner way, or what the challenges are. And it's not about storing keys; it's mainly about how we can verify or establish trust in a key, because that's a major problem. And we kind of talked about the header before, and we're going to talk about a few header-specific claims here that play a crucial role. So in this case, we have a JSON Web Token that's signed with RS256, that's the RSA signature scheme, and we basically have a public or a private key. So that's a bit of the question, like which key has been used to verify which key do we use to verify the signature? Which public key do we use? What if we have multiple keys? How would we deal with that? So let's say we verify a token from Google and we have a couple of keys. Which key do we use? Do we just try them all? Well, probably not. That's where the KID or the KID claim comes into place. And KID stands for key identifier. And it allows you to specify a key using a string-based identifier. So in essence, in this case, we have a list of public keys somewhere, and the generator of the JOT token includes the identifier of the key, the fingerprint of the key, to help the receiver establish trust and verify this with the correct public key. That's very simple, works really well if you have a centralized key store. For example, between your microservices, you can go into that key store, request a public key with this identifier, which is public, so you can easily get it and use that to verify your signature. Or you can call your key store and ask it to verify the signature for you with this specific public key. Awesome. What if we don't have a central key store? What can we do then? Well, JSON Web Tokens, and this is where things get a bit more tricky. JSON Web Tokens also have the ability for you to add key material or key information inside the token itself. In this case, the GKU claim, the JOT spec authors have something with 3-letter abbreviations. It stands for a JSON Web Key URL, basically points to a location where you can find public keys. So in this case, it's an STS from one of my training applications, Restaurate, which is a restaurant review app. And they published a bunch of public keys. And with that key identifier, we can select a specific key from that list of public keys. So that would be one way to retrieve that information. Another way, if you prefer to use TLS certificates, you can also embed a URL that points to a certificate, or you can even embed it directly if you want to with the X5U claim. That's an X509 URL that points to a certificate, in this case, again, from the Restaurate security token service. All right. These two mechanisms sound great, but there's a big problem here. And the problem is that we're using information from a header before we have verified the integrity of that header. And that's a bit of a challenge. So in essence, we're using data without knowing whether we can trust that data, and that can result in a very nasty problem. And this header illustrates exactly that problem. So my malicious training application is called maliciousfood.com. And in this case, we have a JSON Web Token. It has an RSA signature. It points to a list of public keys, and it identifies a specific key. And what's happening here, if your application is a bit gullible, if you just implemented the GKU mechanism, like fetch the keys, fetch the right key, check the signature, everything is going to check out, because the attacker here will be able to give you a token that is signed by its own private key and then publish the public key. And this is really, really bad if you accept it like that. And that's why you can never rely on header information without having verified the integrity first. And this is a problem that we can't really solve. And this is a problem that comes back to bite us with JSON Web Tokens over and over again, also with encryption and so on. And honestly, I don't have a really good solution here. You can try to list a set of accepted keys in your application somehow, like hard code them, or try to check domains before you fetch something, but that's very difficult to get right and very error prone, essentially. So my recommendation here would be to look at other systems, because OpenID Connect uses exactly something like this. OpenID Connect, basically, if you use login with Google, Google is going to sign a JSON Web Token with your information and send it to some receiver. My application, maybe YouTube, or maybe the Eventbrite application, whatever. And Eventbrite, in that case, would have to verify this with Google's public key. And there has to be some trust. And OpenID Connect solves that with a discovery protocol, basically an out-of-band communication where Eventbrite would go to Google's security token service to the .well-known folder /OpenID configuration. And there you will find the configuration of this OpenID Connect endpoint. In this case, that's for my application. And you can see that there's a claim here, JWKS URI. And that says, for this identity provider, the public keys are published in this endpoint. And this is not included in a JSON Web Token. This is done the moment you configure your application to work with this particular identity provider. The application can automatically fetch all of this information without needing to see one single JOT beforehand. Awesome. If you would follow that URL, you would end up at a page like this, where you actually have the list of public keys at that endpoint, and you can see the key identifier claim present here as well. So in OpenID Connect, what's going to happen is your application will use this discovery phase first, fetch the keys, and then when an identity token comes in, it can look up the key identifier, find the right key in the prefetched set of keys, and verify the signature, and then it can decide that it trusts that signature. All right. Seba, you said you had some questions as well, so maybe we can answer a couple of those right now.
Yes, we have some questions coming in. So if you're live, please add those in the Q&A or in the chat. Also on YouTube, just put your questions in the chat here. We have one question here from Bjorn in the Q&A, and he's asking, what are some other common attacks on JOTs?
Yeah, so I would say that most JOT vulnerabilities all come, well, at least for unencrypted JOTs, come down to problems with verifying the signature. So an application failing to verify the signature properly, using a vulnerable library, or having code paths that allow the use of claims without verifying them, using header claims like the GKU, the X5C, something like that, before actually verifying the integrity. Those are all JOT-based problems. I would say once you have succeeded in successfully verifying the signature, at that point, you're working with trusted data, very much like you would pull data out from a server-side session object. And at that point, I would say it comes down to, well, basic to application-level authorization checks. And JOTs are no longer the exact issue there. But in general, it's establishing the integrity and authenticity of the data. That's the main challenge we have with JSON Web Tokens.
Okay. So, and thank you, Philippe, for responding to that. We had an earlier question from Clarence Pinto in the chat. If there would be, is there a noticeable performance impact when you would be using asymmetric key pairs as compared to HMAC?
Honestly, I don't know. I haven't run the numbers, but I can't imagine that there would be. So I know for encryption, there's a huge difference between symmetric and asymmetric, and we almost never encrypt with asymmetric except for a symmetric key to make it easier to encrypt. But for signatures, it doesn't matter much, in my opinion. It's also, well, signatures are not calculated on the full payload, but typically on a hash of the payload. So the input for a signature function is short anyway. Maybe I'll run the numbers in the future and write an article about that if I find some time. But in general, I wouldn't worry about performance. Every OAuth service relying on JSON Web Tokens, every OpenID Connect service relying on JSON Web Tokens is using this exact mechanism. Applications using OpenID Connect use this mechanism, so I don't see any issues in that regard.
Yeah. So, and then thank you. And then and so from what you explained in at the end, there was a question from Konstantin in the chat as well. How about using a custom holder in the JOT header with a serial and do checks at the back end, not the front end? So obviously that would not be a default flow, but a custom JOT flow.
I'm not sure how something like that would work, because you're always struggling with kind of establishing trust in that JSON Web Token. So what we typically see in the OAuth world would be something like this. So an OAuth token There you have a trust relationship between the application handling a JSON Web Token, an access token, or an identity token for OpenID Connect, and the authorization server or identity provider issuing that token. So what you see there is you have the algorithm, which is not really relevant because usually it's very much predefined. We have a key identifier to make it easy to find the key in that preloaded key set from our security token service. And you have a type claim, which today the recommendation is to have explicitly typed JSON Web Tokens. With explicitly typed, we mean that we indicate the purpose of a JSON Web Token. Otherwise, you get token confusion attacks where somebody can give you an identity token and your service thinks it's an access token, and bad things start to happen because that's not how things are supposed to go. So in an OAuth world, the current best practices today that are being developed is add explicit JWT types such as AT plus JWT, which means access token in the format of a JSON Web Token. And that is definitely one of the recommendations that we have here. Other than that, I strongly recommend to either use your internal key management system to retrieve the right keys. That's a trusted location. That's perfectly fine. Or use an out-of-band discovery mechanism to fetch the keys from a known good location before you touch any potentially untrusted data.
Right.
That would be my recommendations here.
Okay, thanks for that. So we have a couple of extra questions coming in through the,
Sure.
the YouTube chat. So if you're seeing this, just add them to the chat window. We still have some time to cover this. So Jan Laan in the YouTube chat, his question is: we spent the last decade telling people to hide HTTP headers because they give out a lot of information to attackers. Should we not encrypt JWTs with all their claims for the same reason?
I would say that depends on who's handling your JWT. So yes, there's in the beginning we talked about that one of the specs here is called JSON Web Encryption. So JWTs actually have support for encrypting. Let's see here, for being encrypted. And actually embeds a signed JWT in an encrypted container, which adds algorithm information. So you get like a 5-part token. But advanced libraries can handle this out of the box. In general, I would say if you issue a JWT, let's say for logging in with Google, Google would create a JSON Web Token and would ship that through to an OpenID Connect flow to the application where you're logging in with Google. If that doesn't go anywhere else, then honestly, it doesn't matter much whether this is encrypted or not. Yes, it contains personal information, but as long as you're not leaking that through refer headers or sending it to third-party services, I don't think it matters much. But if you want to, you can definitely use encrypted JSON Web Tokens. And a lot of advanced specs and mechanisms also try to allow this or try to make this possible. The challenge with encryption, though, is key management. So you'll need to have the public key of the receiver, and only one party will be able to decrypt that token. So, for example, accessing APIs with an access token, if you encrypt the access token, then it's typically only valid for one API, unless you start sharing keys, which you're not supposed to do. So you can see how this becomes a problem, because now you'll need an access token for each API and things like that. But if you want to, you can. But honestly, most situations I've seen should focus on getting authorization right first, and then start worrying about encrypting potentially sensitive data.
Yeah, encrypting everything is not always the best answer, definitely. Okay, Philippe, another one from Wim from YouTube as well. What would be best practice for logging out in the context of JWTs?
Well, I would say that question is not very useful. Well, it very much depends on how you use JSON Web Tokens. So what we see today in single page applications is often called token-based authentication, which is basically just, instead of a session, we throw everything in a JWT and send that back and forth. If you build a session like that, you have no logout mechanism, because all the data lives on the client and there's literally no way to control that. But we have that same problem with a client-side cookie session. So if you use the cookie session library from Express, I think it's cookie session, I'm not exactly sure. It also keeps your session on the client in a cookie object. And it's not a JWT, but it's a cookie with data. And you have no way to really log out there either, because you can't kill that cookie unless the client comes to you, and then you can remove it. That's why in Well, the reason we have this token-based authentication, in my opinion, is because people saw OAuth doing something like this, and they're like, oh, we can take that JOT part out of OAuth and just do something with that ourselves. And all of a sudden, you lose all abilities to revoke sessions, to log out, and so on. In this case, the one we discussed here, the simplification of an OAuth scenario, I would say, what I maybe haven't shown here, I can draw my slides. It's actually pretty cool. What I haven't shown is that this request typically relies on a cookie here. So my apologies, it's with my mouse, so I suck at that, but you get the idea. This uses a cookie under the hood, if it's a browser at least, and that cookie maintains a session between the client and the security token service. And your JOT here is an access token. This access token has a lifetime of, let's say, 5 to 10 minutes. And after 10 minutes, this call will fail. So the client has to go back here to request a new token, and that call will also carry a cookie. The security token service will verify, is your session still valid? Like, oh yeah, you're Philippe from 10 minutes ago. I still know who you are. Awesome. Here's a new JSON Web Token valid for 10 minutes. The client can call the API again for 10 minutes. And that's how we do that with OAuth access tokens. The thing with modern single-page applications and token-based authentication is that they skipped step 1, 2, and 3, and they basically went straight to using JOTs for accessing APIs in a way of a session, and that causes a bit of a challenge to handle things like logout and revocation.
Yeah.
There's a great blog post about that. Let me open.
Yeah, that would be great if you could share that. Just put it in also in the chat window. We'll share
I'll show you right here.
Yeah.
It's literally called "Stop Using JOTs for Sessions," and it's an older blog post from a guy called Yuppie, and it's called Yuppie's Rambling. So it's kind of a very aggressive, hilarious blog post where he says like, this doesn't work because you don't have logout, you don't have revocation. And then people were like, no, but we can like change keys or do this or do that. And then it was like, why don't you leave me alone? And he published a follow-up blog post with a very sarcastic flowchart of why these solutions typically don't work very well. And I recommend you read through this because there's a lot of valid points here. I'm not saying that JOTs are useless. JOTs are very useful, but you typically want some form of a session management mechanism alongside a JOT, like OAuth or OpenID Connect would do in practice.
Yeah, and I think with that you immediately answered also the question of Jeroen in the YouTube chat as well. He's asking what's your opinion on the JOT in authorization header shouldn't be used for session management debate. So that's exactly what you've answered here as well.
Yeah, pretty much. So a JOT in an authorization header in an OAuth landscape would be to represent authority given to a client. That's what you do there. But the actual session is between the browser of the user and the authorization server in that case. The JOT is just a representation of temporary access in light of that session, I would say.
Yeah. Okay, then time for one last question here. I see there's still a question from Joe in the chat. He's asking if it would not be an issue to use a website such as job.io as we have to provide the secret.
Well, yes and no. First of all, in this case, if you have a crappy test secret, like that doesn't matter much. It complains if it's weak. Also, this typically runs completely on the client side. So they say we don't record tokens. Everything is done on the client side. So it's probably okay, but I wouldn't really paste your production JOTs, private key or whatever in here. It very much depends on what you're doing with the JOTs. But in general, if it's really sensitive, if it's production secrets, then yeah, you shouldn't be pasting them in your application. You actually shouldn't even have access to them in the first place. All right. Can I have 2 minutes to wrap it up?
Yes, definitely. Okay? Wrap it up.
All right. So we saw a couple of specs in the beginning, and Jim already gave a spoiler about like, why don't we consolidate a couple of security pointers in a spec? Well, actually, that's what happened last year. There's the JSON Web Token best current practices covering a whole bunch of things we talked about here today, along with some other things. So they state that none shouldn't be accepted, and they outline how you should use JOTs and you should use explicit typing and so on and so on. I would say one of the key takeaways here for me is verify your backend application. So I don't really trust what your you think your code does, as if you haven't verified this. And this is something that I can't stress enough. We saw a code example that looked perfectly valid, but just depending on which library was installed, it either worked or didn't work in a secure way. So what I always recommend for people handling JOTs in APIs is write a test suite. Just take a token that should be accepted and change one letter in the signature. If it's rejected now, good. If it isn't, you have a problem. Generate tokens with alg none and try it out. Yes, it's going to be a bit of work to write that test suite, but it will help you find these vulnerabilities first before a hacker does, which would be bad, or a bug bounty hunter, which would still cost you money because you'll probably have to pay them quite a hefty bounty for finding a vulnerability like that. So that's my main takeaway here. And look up the spec here about the JSON Web Token best current practices. That is a very highly recommended document. All right, and with that, I want to give a quick pointer and a discount code for my online course on OAuth and OIDC. So if you want to learn about this very complex ecosystem of where JOTs are used everywhere, basically, you can definitely check that out and connect with me on Twitter or LinkedIn if you want to stay up to date on web security. That's also perfectly fine. And I hope to see you there. And if you have any questions, I still have a couple of minutes left if Seba wants to keep asking them. Otherwise, this will be goodbye.
Okay, now Philippe will wrap it up here, and thank you very much for doing this. Also, shout out to Jim who has done this remotely from Hawaii very early in the morning. I have like one slide to share with everyone as well. Is that this was the first of a series of virtual chapter meetings from Belgium. In the next couple of months, each third Thursday of the month, we'll be doing the same. So next up will be 18th of March with Steve Springett. He will be doing a virtual chapter meeting on component analysis versus source code analysis. So that will be interesting as well. So I would say check it out. Also, make sure to follow us on YouTube. Subscribe to YouTube. We'll be publishing the recordings afterwards. So Philippe, thank you very much for doing that. And with that, I thank everyone for joining us and looking forward to seeing you next month online.
Awesome. Thanks for having me.
Yeah. Bye-bye. Thanks, Philippe.